Alright, hello class. In this video, what we're going to be doing is we're still looking at volume problems, but we're now looking at the shell method. And what this method does for us is, with the disk method, if you remember, we had to always set up our integral in terms of the axis of revolution. Shells let us do the opposite. Okay, so shells let us revolve around the opposite axis. Okay, so for example, if our integral was in terms of x before, with the disk method we could only revolve around the x-axis, but the shells let us instead revolve this shape around the y. Okay, so that's essentially what shells allow us to do. Okay, to write this idea out a little bit, to make it a little more clear, with the disk and washer method, our integration variable, so if we set up our integral in terms of x, okay, then our axis of revolution, well, we'd have to match that, so we could only revolve around the x. When we set up shells, what's going to happen is if, say, our integration variable is x, here it will be the opposite. We'll be revolving around the y. Okay, so shells can actually make things a little easier, because if everything's already in terms of x and you want to revolve around the y, with the disk method you would have to convert everything into y's first and then revolve, whereas with the shells you wouldn't have to do that. Okay, and vice versa on that. Alright, so let's set this up and then do some examples. I think we've done most of the heavy lifting in the previous two sections. The big problem, or the big issue with this particular method that we add to it, is just when do you use which one. And it really just depends on how it's set up and which way you want to revolve it. Okay, so suppose that we want to revolve this region, say between y equals f of x and y equals g of x. So these are y equals things in terms of x. And we have this region in between here, but we want to revolve it around the y-axis. Okay, so it's going to be a strange little shape here. But what we'll end up with is we're basically just revolving this guy around. Okay, so how we do that in this case is, it's called the shell method. I mean, I don't really honestly know exactly why it's called that, but from A to B what we need is, say, the area of the region that we're talking about for each particular slice. But in this case, our slice looks like sort of a cylinder. Okay, so the slice is sort of a cylinder shape. So what we basically do is, if we look at a simpler one, say something that looks like this, and we want to revolve it around the y-axis, what we do is you can imagine taking a bunch of sheets of paper and making cylinders out of them, and just stacking them together. All right, bunch of these paper cylinders. So each particular slice, so this is still a slicing method, okay? But each particular slice is going to be a hollow cylinder. Okay, and the height, that's going to be the difference between F and G. So let me shift this over. That's going to be F of X minus G of X. Okay, and now to find the area of this slice, right? Well, it's essentially a rectangle, because if we were to slice this right here, cut it, and then spread it out, we would have a rectangle. Okay, so this would be the height, and then this length here, well, that would be the length around a circle. Well, that's the circumference. Okay. Well, the circumference is 2 pi r. So we need to figure out what our radius is going to be, because we have our height. Well, it turns out if we want to find the radius, that's actually going to be the x value partway in between. Okay, so if let me clean this drawing up so that we basically just have the x and then the cylinder that we are creating here. Okay, so this top point comes from f of x, this bottom point comes from g of x, and the radius, well, the radius is x, right? Because that's how far we go from the center. So our circumference is 2 pi x. So the area of this rectangle in terms of x, and again, what ends up being the area of each slice that we create for the general slicing method is going to be, well, it's the width times the height. Okay, so it'll be 2 pi x times h, which is f of x minus g of x. Okay, and so that is where we build our volume formula from. Okay, so more generally, if I have a top function and a bottom function and I want to revolve it around the y-axis, so to find the volume of the region between f of x and g of x on the interval a to b revolved around the y-axis, okay, it's this integral here. It's the integral from a to b of 2 pi x times f of x minus g of x dx. Okay, so it's often written with the 2 pi on the outside. So 2 pi integral from a to b of x times f of x minus g of x. Okay, and we can do a similar thing with y's. So if we want to revolve, say, two functions, right, the left or the rightmost and the leftmost, and we want to revolve this region around the x-axis, well, that volume is going to be 2 pi integral from, in the y case we usually use c to d, so c to d y capital F of y minus capital G of y dy. So it's still, much like before, if the integral's in terms of x, it's going to be a top minus a bottom. If the integral's in terms of y, it's going to be a right minus a left. Okay, but the only thing that's changed here is instead of squaring them, it's either x times it or y times it. And it comes from the fact that we're basically creating rectangles that we spin around. So in this case, our shells look like this, okay, for our y value. Okay. All right, so there's the general idea, the general gist. We can still do this with setups in x and y. So now let's just look at some examples and see what we get. All right, so for our first example, let's let R be the region in quadrant 1, bounded above by the curve y equals 2 minus x squared, and bounded below by the line y equals x. We want to find the volume of the solid generated when R is revolved around the y-axis. Okay, so let's actually take a look at what this shape looks like. Okay, so 2 minus x squared looks something like this, and y equals x looks something like this. So we're looking at this shape here, and we're wanting to revolve it around the y-axis so we get this sort of top-looking shape. All right. So we're revolving around the y. So before, and I'm just cleaning up the graph here. All right, before, to actually do this problem, we would have had to convert this into a y integral and use the disk method. But the problem with that is if we were to do that, for our region, the left side is the axis, but the right side changes. From 0 to 2, so here's 2 in the y, partway through, it changes. So we would actually have to set up two separate integrals to find the volume with the disk method. All right, so we're going to use the shell method instead. So I'm going to take a look at a cleaner version of this shape. Okay, so here's 2 minus x squared up here, and here's y equals x down here. All right, so here's the height of the shell that we would be spinning around. Okay, so what we need to figure out is this value right here, because I know the x goes from 0. I need to find the next x. So like always, we're going to set these two guys equal to one another. I'm going to move things over to this side so that I have 0 is equal to 2 plus x minus, oops, plus x squared. Oh, I messed that all up, didn't I? Let's do it this way. X squared plus x minus 2. All right, so that should factor into what, x plus 2 times x minus 1. So x is equal to either 1 or negative 2, so that should be x equals 1 there. Okay, so the volume, right, it's going to be 2 pi times the integral. Well, now we have 0 to 1, so it'll be 0 to 1 of x times our f of x, so the top value, so that's 2 minus x squared, minus the bottom, so our bottom here is x dx. Okay, in some ways it's a little nicer, in some ways it's not. We don't have to square anything. I'm going to write it like this so it's in order. We don't have to square anything, but we do have to distribute that x. Okay, so we get 2x minus x squared minus x cubed dx. All right, then we calculate this, or integrate. Don't forget your 2 pi, but you'll get 2 pi. Then you'll get x squared minus 1/3 x cubed minus 1/4 x to the 4th. And we'll evaluate that from 0 to 1. Okay, so it'll be 2 pi. And really we can just plug in the 1. It'll be 1 minus 1/3 minus 1/4. Alright, so I'm going to put these all over 12. So it'll be 12 twelfths minus 4 twelfths minus 3 twelfths. Okay, so that should be 2 pi times 5 twelfths, I think. Yeah. Okay, and then the 12 will cancel with the 2 and leave us 6. So we'll get 5 pi over 6. Alright, so not that bad. Okay, now this problem would have been bad if we tried to do it with the washer method. However, if you would still get the right or the same answer. It would just be a lot more work to get there. Alright, if we actually tried this with the disk method, I do want to, now that I think about it, I do want to show it. Just to show that it's not like it's wrong, okay, to use the disk method here. It's just trickier, okay, because we would have to get this in terms of y. So we know that y is going from 0 to 2, so we have that part figured out. But remember, it's right minus left, and that changes here. So we need to figure out what y that happens at. Okay, so to start with, we need to switch this over to an x in terms of y's, right? Y functions. So we can start by getting y minus 2 equals to negative x squared. So 2 minus y is equal to x squared. And so x is equal to plus or minus the square root of 2 minus y. Now we're going to choose the positive one. Mainly because, well, we're in quadrant 1 and everything needs to be positive. Okay, so there's our right side just for here, though. And for our left side, well, that one's not that difficult. We just kind of say, oh, x is equal to y. Okay, but we need to set these equal to one another and see where they intersect. We could plug 1 in to one of these, and actually I think that's what I would do if I hadn't already solved it up here. So if we've already solved for the x value here, so we could actually plug that into one of these and get, in both cases, that y is equal to 1. But I'm pretending now that I approached this with only the disk method and I hadn't done that yet. Okay? And that's just to show that this is a trickier thing to solve for. We could find the intersection here, but we might not have thought to do it in terms of x's first when we're trying to get our integral in terms of y. So what you have to do is square both sides, okay, and then you end up getting the same thing we got before, okay, just in terms of y's. So that means we'll get y is equal to -2 and y is equal to 1. So this is y equals 1. So I've not been drawing this to scale at all. Okay, so to set up the volume with the disk method, all right, I would actually have to do two separate integrals, one here and one here, because I would need to do pi times the integral from 0 to 1 of, and here is our left side, or our, excuse me, I keep doing that. Here's our right side here. It's the x, sorry, not x, y squared dy. Okay, then plus pi times the integral from 1 to 2 of, now it's this right side squared. So it'll be 2 minus x squared all squared. And I keep doing that. It's the y one. So sorry about that. It's this one. The square root of 2 minus y. And then that squared dy. Okay. So we'll get pi times, this will just be the integral of y squared. Then I'll get pi times the integral from 1 to 2. And here, that actually does simplify nicely as just the integral of 2 minus y dy. And now I can just start integrating. So I have pi times here, it will be 1/3 y cubed between 0 and 1. And pi times here will be 2y minus 1/2 y squared between 1 and 2. So not only do I have two integrals, but versus just the one integral we had up here, but the integral we had up here, the limits were nicer because now the first limits are fine with the 0 to 1, but this one has 1 to 2, so we have trickier limits to deal with. All right, so this will just be pi times 1/3. All right, that's not that bad. And over here, we'll get pi times, now we plug in the 2. Okay, so let me put some parentheses around that, and then we'll plug in the 1. So when you plug in the 1, you'll get 2 times 1 minus 1/2 times 1 squared. I'm being very explicit about this. All right, so we'll get pi over 3 plus pi times, here we'll get 4 minus 2, okay, and then we need to be sure we change the signs over here, so it will be minus 2, then plus 1/2. Okay, so we'll get pi thirds plus pi halves, which will be, when we add this up, 5 pi over 6. So, as you can see, we do get the same thing, okay, but in a much more convoluted path to get there, okay? Whereas with shells, we see it's a much more streamlined way to get there. So if the way you want to set up your integral doesn't match your axis of revolution, well, then you're probably going to want to use shells. Okay, so for this one, let's find the volume of the solid generated by revolving R around the x-axis. And R is the region bounded by the curves y equals the square root of x, and y equals 2 minus x, and y equals 0. So square root of x looks like this, okay? And 2 minus x, well, so for 2 minus x, it's here. And let me... Okay, so it may be confusing to figure out which one they're talking about, right? So here's y equals square root of x, and here is y equals 2 minus x. A fair question is, well, okay, are we talking about this region in here or this region in here? And how we do that is we then use this curve. The y equals 0 is here. So the region that is actually bounded by all three is this one. Okay, so it looks something like this, and we want to revolve this around the x-axis. Okay, now I'm going to use shells, and I'll show you why I want to use shells. So I want to use shells because if I try to do this with the disk method, it's already set up for that, essentially, because these are already y's in terms of x. However, when integrals are in terms of x, they go bottom to top, but as we can see, the top function on this side of the region, okay, is this one, but then on the other side here, it changes. So it would require two integrals once again. So we'd have to find where this breakpoint is, and we'd have to, you know, set up the two integrals. So what I'll do instead is use shells, and to use shells, we'll set it up in terms of y's instead. And when we do that, if we compare the right side and the left side, they don't change. The right is always this function here, and the left is always this function here. And y goes from 0. We just need to figure out what this y value is there. Okay? So I'm going to start converting this over to an integral in terms of y so I can use shells. So here, this conversion shouldn't be that bad. Y squared is equal to x. This one shouldn't be that bad either. You'll get y minus 2 is equal to negative x. So x is equal to 2 minus y. Okay? Then we just need to figure out where they intersect here. Okay, so to do that, like always, we will set them equal to one another. And we'll get y squared plus y minus 2 is equal to 0. I promise they will not all, they won't all be just like this. That is a strange little coincidence there. So it turns out this is y equals 1. All right, and now I'm ready to use shells. I've got everything I need, right? The volume will be 2 pi times the integral from 0 to 1 of y times, now it's the right function, so in this case the right function is the 2 minus y, so it'll be the 2 minus y. There's our right, and I need to do minus left. So the left is the y squared. dy. Alright, so we'll get 2 pi times the integral from 0 to 1 of this will be 2y minus y squared minus y cubed dy. And we'll get 2 pi times, now when we integrate, we'll get y squared minus 1/3 y cubed minus 1/4 y to the 4th. And since we've done this one already with pretty much the exact same numbers, we get 5 pi over 6. Okay, if you think about it, this is actually exactly the same shape. We're just we're orienting it in a different direction. Okay. All right, let's look at a different one that maybe is not the exact same shape, just reoriented. All right, so for this example, we want to find the volume of the solid generated by revolving capital R around the y-axis, and R is the region bounded by two parabolas, x squared minus 6x plus 10 and negative x squared plus 4x plus 2. So these parabolas, when you graph them, look something like this. Okay, the negative x squared one is the one that opens downward. Okay, while the one that opens upwards will be the positive x squared minus 6x plus 10. And we want to revolve this region around the y-axis. Now, we're going to want to use shells here because these are already functions of x, right? This is an f of x, this is a g of x. I don't want to try and convert these as a x equals something, right? I just don't want to do that. That sounds awful trying to do it in this case. And then if you did it, you'd have to set up two separate integrals. And actually, I didn't really draw this to scale because they don't actually, when you look at these, if you look at the graph of these, it's not like it's actually balanced this well. So it might actually look something like this instead. Okay. So that these two don't actually line up. So it would actually be, if we wanted to use the disk method here, it would be 3 integrals we'd have to set up, and we'd have to convert these over into x equals functions, which would be a nightmare and be no fun. So instead, we're going to use the shell method because I have this set up the way we needed already to do that. Okay, so all I really need now, I have my top and I have my bottom. I just need my A and B. Okay, so we're going to set these guys equal to one another and see what we get. So I'm going to take this negative x squared plus 4x plus 2. I'm going to set it equal to, I think I put a negative down there when I shouldn't have, a positive x squared minus 6x plus 10. All right, so I'm going to move everything over here to this side so that I get 0 is equal to 2x squared. All right, so I'm going to subtract the 6, so it'll be minus 10x, and I'll subtract the 2, so it'll be plus 8. And then I'm going to divide everything by 2 just to simplify this through. So we get 0 is equal to x squared minus 5x plus 4. All right, so this should factor, I want factors of 4 that sum up to be negative 5, so I'm thinking x minus 4 and x minus 1 will do the trick. All right, so x is equal to 1 and 4. And that makes sense, right, with what we're doing here. So that should be everything we need. Now we can set up the volume. Since we're using shells, it'll be 2 pi. And then the integral from 1 to 4 of x times, now it'll be the top, that's this negative x squared plus 4x plus 2, minus the bottom, so that will be x squared minus 6x plus 10. Now, I do suggest doing this every time, but what you're going to see is some very similar stuff show up when you do this, right? So the negative x squared minus x squared. All right, so that's familiar. Let me just distribute this negative. All right, now we'll simplify. All right, so I'll have negative 2x squared. We'll have plus 10x and minus 8. All right, so you'll notice that's pretty much what we had here. And in fact, they all share a 2, so we can actually factor a 2 out to get a 4 pi out here. That's not really necessary, but might help. And we can distribute the x. So we'll get negative x cubed plus 5x squared minus 4x. All right. Now we can just integrate. Right, this will be negative a fourth x to the fourth plus 5/3 x to the third, and since I'm integrating, of course, I should get rid of this. Minus 2x squared, and we're going to evaluate this from 1 to 4. And I am going to, well, I'll go ahead and plug in this part and then just jump to what it is actually equal to. Okay, so we plug in the 4. And unfortunately, we don't have 0 as our lower term, but 1 is also nice. And this is not going to be pretty, right? This is not a great looking thing here, but that's all right. Given enough time, we can figure it out. So let's see. Okay, after using my handy little calculator, what I've found is that all this stuff in here ends up coming out to be 45 over 4. So the 4's cancel and we get 45 pi. All right. Sounds good. All right, we've got time for one more, it looks like. So let's find the volume of the solid generated by, revolving R, blah, blah, blah. This time about around the x-axis, and R is the region bounded by these awful looking functions here. All right, so this is actually one. Right, I want to revolve this around the x-axis, and just looking at this, it looks pretty horrible, right? So here's y equals 1, and the square root of ln x would look something like this, I'm guessing, and the other one would look, it might look something like this. Okay, so we're talking about this region here that we want to revolve around the x-axis, and it kind of looks like, actually, I would want to use disks, two integrals. if I wanted to use disks. And the reason I think that is because I know with the disk method I would square these, so that would make that a lot nicer to deal with. However, with using shells, I'd only need to set up a single integral because the left and the right would end up being pretty much the same. Okay, so, and I already know the limits, it's 0 to 1. So I'm going to set this up with shells. I just need to solve these guys in terms of, well, x. So for the y equals the square root of the natural log of x, we'll square both sides. So y is equal to, or y squared is equal to the natural log of x. Then e of both sides. Right? To get x is equal to e times the natural log, or sorry, e of y squared. And for the other one, you do the same thing. If y is equal to the square root of the natural log of x squared, well, one thing we can do, okay, is we can bring this power outside right now. So when we square both sides, we get y squared is equal to, jumping the gun there, 2 ln x, and then we can divide both sides by the 2. Okay, so we'll get e to the 1/2 y squared is equal to x. Okay, so which is which though? Well, this one, notice we're multiplying by 2, so it will be this side. So this is the e to the 1/2 x or y squared, and then the right side will be e to the y squared. Okay. This is one where I would understand if you needed to use a graphing calculator to kind of figure out what's going on. All right. All right. Now, we have everything we need, right? The volume is going to be 2 pi times the integral from 0 to 1 of y times, so it will be the right side, e to the y squared, minus the left side, which will be e to the 1/2 y squared dy. Okay. So we're going to use our quick u substitution. It's been a while. Okay, and you'll see why in just a second. It's going to make things a little easier for us. I'm going to leave this y here, but then integral of, and I don't know why I keep forgetting to do that. All right, so I'm going to leave the y here, and then the integral of e to the stuff is itself, but then we divide by the derivative of that stuff, and we'll do the same thing here. It'll be e to the 1/2 y squared over, now it'll just be y down here. We're going to evaluate from 0 to 1, and these y's here cancel with this y here, so that is exactly what we need for the quick u substitution. And I love quick u substitution for definite integrals because you don't have to, you know, it's a lot less work switching back and forth and all that. So anyway, now we'll plug in the 1. So it'll be e to the 1 over 2 minus e to the 1/2. Okay, so there's plugging in the 1. Okay, plugging in the 2 though, or not the 2, I'm sorry, the 0. Well, e to the 0 is 1, so this will end up being 1/2 minus 1. So with e and cosine and various things, when you plug in 0, it doesn't just go away. Okay, so we'll get 2 pi times e halves minus e to the 1/2, which is odd. This will be a -1/2, so it'll be plus 1/2 And honestly, feel free to leave your final answer just like that. Okay? So I think I've thrown enough brain melters at you for this particular video, so I will catch you all in the next one. Cheers.